So our next presenter is Kelsey Young from the NASA Goddard Space Flight Center, and she will be presenting on developing advanced EVA informatics for field portable instrumentation and science operations during crewed planetary surface exploration.
That was a mouthful, thank you. First of all, I'd like to thank the session chairs and Survey Central, as well as the organizing committee for the session and for inviting me to speak at the session. Switching gears a little bit, I first want to say thank you to a huge team of co-Is on the RIS'E Survey team, led by Tim Glotch out of Stony Brook, as well as some of the NASA analog projects I'm going to be talking about today. And what we want to do today is talk about prepping for the next generation of crewed planetary surface exploration with the Artemis program, which we've heard a lot about this week. What are informatics? Well, astronauts need to process a large volume of information during EVA, things like how to stay alive, how much consumables they have left, and then of course, science information and data as well. Informatics can help crews view that information real time. They can help crews view navigation information, procedures, help with troubleshooting anything that goes wrong. And astronauts have used informatics during all the way back through Apollo. The pictures here show an image that the Apollo 17 commander had visible to him during an EVA, showing reminders about the traverse plan. And on ISS, on the International Space Station today, astronauts are able to use the things like the cuff checklist that's shown here. So you can actually look down at your wrist and see basic EVA plans, troubleshooting help, abort procedures, anything that you want to just be able to look down at as a quick reference on your wrist. Development's currently underway for informatics for the Artemis program, and that's development is centering around a number of different areas, including content, what needs to be on those informatics, what do we need to support our Artemis astronauts, what format and technology is that support going to be in. We heard an absolutely phenomenal talk by University of Michigan team earlier today talking about one idea, and I know that there's a talk right after me that I think is going to touch on this a little bit. And what I'm going to talk to you about today is some ongoing field testing we have to look at the development of informatics to support EVAs. So before I get into the RISE-2 survey work, I want to talk a little bit about setting the stage with some underwater testing we've done. And the reason we've done this testing is to simulate high fidelity mission environments to understand exactly what the drivers are in developing informatics to support science motivated EVAs. So the NEMO project includes astronauts, scientists, and engineers living underwater in an underwater habitat for 1 to 2 weeks at a time to simulate what it's like to live in space. They don't just live inside their house underwater, they conduct simulated EVAs outside of the habitat to simulate astronauts doing EVAs on the moon and Mars. Among many things that we test in NEMO is the use of marine science as a proxy for doing geology on the lunar surface. While sampling corals is not quite the same as sampling rocks, the procedures and the hardware used to do it are actually really similar. What the informatics capabilities were that we tested in NEMO is the use of cue cards, or this hyperlinked file that the crew accessed via an underwater iPad that allowed them to view procedures, traverse plans, the daily traverse map, procedures for science, as well as pioneering tasks. And we also evaluated the use of a heads-up display with a partnership with the US Navy that you can see in a picture on the bottom right there to evaluate how HUDs can be useful to display scientific information. The second underwater platform that we tested in is NXT, or Neoteric Exploration Technologies. That includes the exosuit and the dual deep worker submersible that you see on the bottom left as an analog for astronauts in a spacesuit and astronauts in a two-person rover traversing over the lunar surface. We actually did use heads-up display in both the EVA suit and the rover analog in this test, which is really interesting to use it not just when you're out on EVA, but while you're inside your rover as well to see how that can be useful. And the data that we tested there included navigation and tracking. You were able to see where you were versus your traverse plan versus where the suit or the sub was opposite you. You were able to view science procedures, images taken on prior traverses, as well as real-time imagery from yourself and the other craft in the water. And then we really proved and demonstrated the capability of these heads-up display capabilities. So some takeaways that I think are relevant to set the stage for RISE-2 are that the crews really did find the informatics useful if they didn't impact or restrict your movement or reduce efficiency. On the previous page, you saw somebody wearing the goggles inside a spacesuit helmet, which can be really difficult in an already restricted environment. But barring those difficulties, the crews really did like the use of informatics. They didn't really need them for traverse maps, basic sampling procedures, and those types of informatics were not really frequently accessed on EVA. However, what they did find really useful was navigation and tracking. An example of some of the traverse maps that we had real time are on the bottom right, but also viewing instrument procedures and data real time. I'm not going to spend time talking about the use of navigation and tracking information today because this is a science-focused meeting. But what we really want to highlight from this is that in this really dangerous environment, an underwater environment, which is very similar to operating in outer space, these informatics really did provide a useful resource, and all of the crew feedback came back that especially in the area of instrument procedures, viewing data, and helping understand the science environment, informatics can really shine. So we seek to sort of evaluate that with the RIS'E survey team. We've been working at the Kilbourne hole and the Potrillo volcanic structures out in New Mexico for a number of years with the RISE team and now the RISE-2 survey team. It's a great analog for the Moon and Mars and was used all the way back to the Apollo days. The objectives of these teams in part focus on the deployment of field portable instruments and how to integrate these really valuable tools into EVAs. We've completed through the RISE project a series of EVAs at Kilbourne Hole to develop several field portable instruments like the ones you see listed here that give you real-time geochemistry, mineralogy, overhead imagery, and a lot of other great tripod-based analyses in the field. Want to highlight the partnerships that we've had with the Espresso survey team and moving into the future with the Geode survey team to really help flesh out the use of field portable instruments, and with the Geode survey team bring in geophysics to bear on these really interesting problems. So with RISE, we had several simulated EVAs at this lunar analog site and deployed instruments in an effort to understand how instruments can be useful, answer science questions about the area, and start to flesh out the requirements for informatics. So if you're not familiar, field portable instruments can be really useful in both high grading samples to decide which samples you want to bring back to Earth, as well as just increasing science knowledge during real-time exploration. However, they do generate a lot of data. And so we need to figure out a great strategy for incorporating that data into the tactical and strategic execution of EVAs and how to show crews those data without getting in their way of tracking consumables and staying on timeline. So as you can see here, we just have some examples of the types of cue cards modeled after Nemo that we use to display to the crew, which was made of one geologist and one astronaut, to say, here's the data you've collected with your field portable instruments, and here's how it fits into the broader context of the science questions you have for this site. And so this is really building toward the future. We've really done a lot with the underwater analog testing, as well as with the initial EVAs with the RISE-1 survey team. And RISE-2 really hopes to build off of the success that we had with RISE-1 to continue the development and the deployment of in situ informatics capabilities. We have the great fortune of working with Ben Feist. If you've ever checked out apollo17.org, if you can, I encourage you to do so. And really what we're doing is taking the field portable instruments, some of which the data, some of which I show across the bottom of the screen here, to demonstrate strategies for how to spatially and temporally view and manage and visualize data to support science-driven EVAs. So what we're doing is not just developing cue cards like you see here that we actually were able to use with the RISE-1 EVAs, but figuring out how to integrate that software real time to evaluate how crews view and visualize data and what role mission control plays in that data assimilation and what supporting informatics those mission control teams need to have to be able to support those science-driven EVAs. And so across the bottom, we have just a few examples of a number of our instrument teams from our great instrument scientists that show exactly the type of data that the crew members were able to access.
You're at 8 minutes.
Thank you. And Ben Feist is able to really help us demonstrate strategies for how to integrate all of those data streams together to not just support the crew's real time, but to support the mission control capabilities back on Earth for those scientists to be able to assist the astronauts in real time exploration. So this is my final slide, and I want to make a couple points. Informatics really have the potential to increase the efficiency of doing science on EVA, but it's critical to design a system that doesn't interfere with an astronaut operating in an already dangerous and dynamic environment. The underwater testing we did really highlighted the role that informatics can play. We learned a lot about what's useful and what's not useful, and the major takeaway there was that informatics really can play a valuable role as long as you can design a system that doesn't impinge on an astronaut's movement. The RISE survey team is playing off of initial EVAs at the Kilbourne hole area with the RISE-2 project, which will be testing designs in conjunction with Ben Feist's platform to support scientifically motivated EVAs over the course of the next 4 field seasons, COVID notwithstanding. And I also want to end with a look to the future. We heard a little bit about this with that wonderful University of Michigan presentation, but NASA's working on concepts for advanced heads-up display capabilities, not something we've ever done before on EVAs. ISS and Apollo used sort of an NFL quarterback's cuff checklist to view data and procedures. We're working on more advanced concepts for Artemis EVAs, but it's up to us in the science community to determine what data we want the crew to see real time, what procedures are critical, what troubleshooting assistance we want to provide to them. And we really want to be able to enhance the ability to do science and not detract from the efficiency of an EVA. And lastly, I'll just end to mad props and thank you to the RISE and RISE-2 teams, as well as the NEMO and NXT teams, as well as NASA and Survey for funding this work. Thanks.
Thank you, Kelsey, for that presentation. We have one question from Gavin, who asks, along with Kilbourne, are there other sites the RISE-4 and RISE-2 teams are considering to simulate instrumentation and test lunar and Mars EVAs?
Great question. Yeah. There's a lot of analog sites that our team and other teams funded by Survey and funded elsewhere in NASA do field work. Gavin, I know you're familiar with those. The RISE-1 team did several simulated EVAs out on the Big Island of Hawaii at the Kilauea volcano. So we have that history to rely on. RISE-2 fieldwork is predominantly going to focus around the New Mexico area. But there are, of course, and Gavin, you've been a part of this as well. There's fieldwork taking place in analog environments all over the world, especially as we prep for the Artemis program.
I have a question. Have you done any research into how much of this information should be relayed to the astronaut versus relayed to ground stations?
Yeah, that's a great question and a tough question, and it comes in multiple flavors. A lot of that testing is ongoing right now. We're heavily integrated with the mission control operations teams already to start to flesh out those concepts because this is a EVA paradigm that we're not used to operating in. ISS EVAs are, you have rigorous traverse plans that say go to from handrail A to handrail B in this order at this time. That's not the paradigm of doing scientifically motivated EVAs. So there's a lot of ongoing work and analog testing to be able to drive out what mission control needs to see versus what the crew needs to see. And the crew are the best geologists on the lunar surface. They're going to be really highly trained, and we don't want a lot of this instrument flow to impinge on what they're doing and set them back on the timeline. So it's going to be a really coordinated dance between support from mission control and really highly trained crew members. And it takes a lot of practice, and that practice is already starting.
Thank you. And I think Thomas Orlando has one last question. He asks if the heads-up display will display real-time information versus the latency to a ground station.
Yeah, great question. And a lot of that depends on the communications architecture that we have with the Artemis program. I will say that a lot of what's being talked about as we scheme out what this might look like will be that the crew will be able to access it. If the science team decides that that's something that's useful, they'll be able to access it real time as they're closer without the latency to the actual instrument itself than what the ground control team is going to see. But the simulations that we're already doing do incorporate that small latency time delay back to mission control. So the hope is that whatever data we want the crew to see, they'll see it real time unless it's something that requires ground control team processing before they see that processed data. So like I said, it's a tightly choreographed dance, and we're really excited to start working out these problems. And thanks for the great questions.
Thanks again, Kelsey, for that presentation.